All right, so we continue. Perhaps a way to explain this and seeing this blob model in another way, which could be perhaps via this simple example. So suppose that we are at the surface of the Earth, right, in some terrain which is not perfectly flat. It's a bit, going up and down. Okay, so there are local fluctuations of a couple of meters vertical in our terrain and on the scale of few meters. Okay, it's only if we move sufficiently far. Suppose that this is the side of a hill, but the hill is gently. Only if we move sufficiently far from here, is that we see that actually this is not fluctuating slope with average height constant, but is actually going down. So we have two fluctuations. Well, we have the local fluctuations of typical ups and downs at the local scale of a few tens of meters. But if we move away 100 meters, 200 meters, then we see that we are actually gently going down. And this is similar to the concept of the blob. In a blob, we have to move on the distance size of the blob to actually notice that our polymer is not an ideal polymer and at rest, but it's actually stretched. Okay, there is a force there, so there is a scale, and the way there is a way to characterize this scale here by looking at the intersection between these two curves, 1 and 2. And if I look at the intersection, I can solve for g. So the math is very simple. Set 1 equal to 2, and this gives the value of g at which this happens. Okay. By the way, this is a 9. This is not a g. This is number 9. Okay. So don't confuse it. So if I set the two equal and I solve for g, so I want g a squared equal to g squared a squared divided by 9, but actually I will skip numerical factor. Here we are working on a scaling, typical scaling arguments. We forget the numerical factor 9 here to make the relation simpler. So we have f a divided by kbt squared. Okay. We simplify this. We simplify the a squared. We simplify the 2 and we get the 1. So we get an estimate of g. G is roughly scales as kbt divided by f a. Okay, squared, right? Or we use the law that scaling law that is here. We find that the size of the blob, psi b, is a square root of g. A square root of g gives exactly kbt divided by f. Okay, so you see that this is a fundamental relation. This is psi b is the size of the blob. It's inversely proportional to the force and with kbt. Okay, kbt divided by f is a characteristic length, and we identify this with the length, the size of the blob. Okay, so within that length, I can use ideal polymer scaling laws, but beyond that length, I have to use take into account that there is a force. Okay. All right. So that was there was the part for on the ideal polymer. So what happens now? Okay, if I start with f equal to 0, actually all my polymer, the polymer is ideal. This is the first monomer, and this is the Ramon-Moog. Okay, this has a characteristic radius that scales as a square root of n. Okay, if I start stretching the polymer and I have I put an f larger than 0, then my polymer separates into blobs of a certain size. Okay. The higher is f, the smaller is the size of the blob. So if I start from small f, my polymer will have large blobs, blob number 1, blob number 2, blob number 3, and so on. This is the characteristic blob size is large. Okay, this is the characteristic blob size at small force. But as the force becomes large, this F is large, then my blob size is smaller and smaller. I have the first blob, the second blob, and so on. Difficult to draw, but I hope that this gives a bit the idea. Of course, then it's a bit more stretch and so on and so on. Okay. So you see that you recognize a characteristic length scale here, psi b, that is much smaller, and it goes as 1 over f, 1 over the force. Okay. So one can ask, so one force that gives me a blob of the same size of an ideal polymer. Okay, so I ask, what is the force, F star, the force such that the blob size is actually the same size of the ideal polymer. Now this is a small force, such that actually the whole small force such that I start from an ideal polymer, I start stretching it a little bit, but not such that I really see a manifestation of the stretching, such that actually my two endpoints remain within the blob within the ideal polymer radius. Okay, so then it's easy. That psi b is given there. So I find f star. It's simply given by reversing that relation. So f star is given by kbt divided by a n to the power 1/2. Okay. All right. Okay, so this is a force, actually, force scale that you see that it's decreasing as the length of the polymer is becoming larger and larger, is the force scale at which I start seeing a manifest effect of stretching. Okay, when I see really that my polymer is not a sphere uniform blob, but there is some stretching at the end point. Okay, so you can ask yourself, and actually what we want to do next is to calculate the value of this force, for instance, for a piece of DNA. Take a DNA with, so it has 15 kilobase pairs. Okay, it's a sequence of 15 kilobases. Okay, so you have sequence A, T, C, and G, 5,000 of these letters on a sequence. All right. So we know that the persistence length of the DNA is 150 base pairs. So it roughly means that I can consider my sequence, my DNA, like a set of random freely jointed chains of length each of 150 bases. Okay, so it means I can consider my DNA as a segment, so as a sequence of n, which I obtain by dividing 50 kilobases divided by 150, okay, base pairs, okay, and this gives me about 100. That gives me exactly 100. Okay, 100 segments. So I can consider this piece of DNA as made by 100 of these segments, each of length A. A is the persistence length, is 150 bases. In length is about 50 nanometers. I hope that this is visible. Okay, so you can apply this and ask what is the F star for this piece of DNA. Okay, so I can erase this part. So what is F star for this piece of DNA? So we know that KBT is equal to, for T at the room temperature, is roughly 4 piconewton times nanometer. And we divide this by A, which is 50 nanometers. Okay. And the square root of N, which is 10. Okay, this is a number. So we have 4 divided by 500. We approximate this as 5 divided by 500. This gives us, okay, the nanometer goes away. This gives us a 10 to the minus 2 piconewton. Okay. So what is this 10 to the minus 2 piconewton? At this force scale for my 15 kilobase DNA, actually, it's not really significantly perturbing the the ideal structure of the polymer. Okay. So I have a piece of DNA of 15 kilobase pairs. At 0 force, it's a random coed, like this. And if I apply a force up to 10 to the minus 2 piconewton, right? So this is a 15 kilobase pairs DNA. Up to a force of 10 to the minus 2 piconewton, this is actually not significantly stretched. So I will still see roughly the same blob that I observe, the same spherical structure that I observe at 0 force. Okay, it's only beyond the force is much larger than 10 to the minus 2 that my segment will, my DNA of these 15 kilobase pairs will significantly be stretched. Okay.